You know the feeling. You get a brand new phone, and the chip inside is just unbelievably fast. Your laptop chews through tasks that would have been impossible just a few years ago, but that little battery icon, it still seems to be draining at the same old frustrating pace. It's got to be one of the biggest disconnects in all of modern tech. Right? It's a totally fair question. We've been trained by Moore's Law for, what, a half a century now to just expect this incredible exponential growth in our gadgets. So why does the one thing that powers it all feel like it's stuck in first gear? Well, as it turns out, the answer gets to the very heart of the difference between the neat, orderly world of silicon and the messy, complex world of chemistry. Okay, so let's just look at the two side by side. On the left, you've got the legend, Moore's Law. It's an absolute rocket ship of progress, doubling performance every couple of years. And then you've got batteries. It's not a rocket ship, it's more like a slow, steady hike up a mountain. I mean, a 5 times improvement in 30 years is nothing to sneeze at, but it's just not even in the same universe as exponential growth. And here's the absolute crux of it. Moore's Law works because you can just keep shrinking transistors and packing more of them onto a chip. It's an engineering and physics problem. But a battery, that's a whole different beast. It's a chemical engine. You can't just shrink it. To make it better, you have to fundamentally change the actual materials doing the work inside. You're wrestling with the periodic table, not just geometry.
You know, I love this quote because it gives us a much better way to think about this. Forget a smooth curve. Battery progress looks more like a staircase. We spend years, sometimes decades, grinding away making tiny little improvements on one level. Then, bam, a breakthrough in material science happens and we jump up to a whole new step. That was lithium-ion. And now we're on that step, grinding away again, looking for the next big jump.
So what exactly makes this grind so incredibly tough? Well, it really comes down to 3 huge overlapping challenges that scientists are battling every single day. Let's dig into what they are. First up is just raw energy density. And this number, well, it's pretty humbling. For all its problems, gasoline is an amazing way to store energy. We're talking 10,000 watt-hours per kilogram. Our very best, top-of-the-line lithium-ion batteries, they top out around 400. That is a 25 times difference. You don't close a gap like that by tweaking things. You need entirely new chemistry, plain and simple. Hurdle number 2 is all about speed. Think fast charging. When you charge a battery, every single lithium ion has to go on this little obstacle course. It has to strip off its little solvent shell, push its way through a gooey protective layer, physically wedge itself into the anode material, and then hope that all its neighbors are doing the same thing uniformly. Now, imagine telling billions and billions of these ions to do that obstacle course in just 15 minutes. It's a recipe for a traffic jam, and that traffic jam can cause real damage and major safety risks. And that brings us to our third and maybe the most brutal hurdle, making these things at massive scale. A big gigafactory is spitting out almost 70 battery cells every single second. It is this high-speed dance of coating and stacking and rolling materials that are thinner than human hair. And at that speed, one tiny mistake, a microscopic speck of dust, a layer that's off by a hair's breadth, can create a hidden flaw that leads to, well, exactly what you see here. A total disaster. And that list of potential flaws is just terrifying. We're talking about things you could never see with the naked eye. Tiny tears in the electrodes, little folds in the separator, microscopic metal burrs. In fact, you might remember the big Chevy Bolt recall. That was traced back to 2 of these tiny defects happening in the very same cell, a torn anode and a folded separator. The challenge of making sure that not one of those things happens in the billions of cells being made is just monumental. So with challenges this big, the industry is having a bit of a reality check. The new thinking isn't about finding one single super battery that's going to solve all our problems. No, the future of energy storage is all about using the right tool for the right job. And this quote from Dr. Gogotsi just nails it. The battery you need for an electric airplane is completely different from the battery you need for grid storage, which is totally different from the one in your smartwatch. We don't need a silver bullet. We need a whole toolkit. And this is a sneak peek at what that toolkit is starting to look like. You've got sodium ion, which is perfect for huge, cheap grid storage because sodium is everywhere. You have the holy grail, solid state, for high-performance cars and planes if we can solve its own traffic jam problems. You've got super safe zinc batteries, and then lithium metal, which is the ultimate in energy density if we can just figure out how to keep it from being dangerous. The key thing to see here is that these aren't really competing with each other. They're complementing each other. So, if the future is this big, diverse toolkit, the question is, how do we build it faster? How do we actually engineer that next big jump up the staircase? Well, the answer lies in a whole new generation of incredibly powerful tools that are letting scientists work smarter and faster than ever before. First up is AI. For decades, battery development was this slow process of trial and error. Mix some stuff in the lab, see what happens. But now, as Dr. Xu says, scientists are using deep learning to design and test millions, even billions of potential new molecules inside a computer before they ever make them in the real world. AI can predict which ones will work and which ones will fail, which just slashes the development time. And at the very same time, we can finally see what's actually happening inside a battery. Tools like cryo-TEM, which Dr. Meng calls a game changer, literally let scientists flash freeze a battery while it's running. This gives them a perfect atomic-level snapshot of how those ions are moving and how those critical failure points form. For the first time, we aren't just guessing what's going on in there. So you start to put all this together, and you can see why there's so much excitement. We've got AI designing brand new materials from scratch. We've got advanced imaging that lets us watch those materials work at the atomic level. And we've got a flood of new building blocks, like these things called M-zines, that give us totally new ways to build a battery. These are the tools that are going to help us finally tackle those big three hurdles: density, speed, and quality. So, in the end, why don't batteries follow Moore's law? Because they follow the laws of chemistry and physics, which are just a lot messier and more stubborn than the laws of silicon. But the path forward is becoming so much clearer. It's not about waiting for some single miracle battery to save us. It's about building out this incredible new toolkit of specialized solutions. The only real question left is, how fast can we build it?